can welcome Íñigo Aréjula from the BSc. He is HPC quantum software engineer, and he will give a talk about dynamic resource management in quantum circuit simulations. Thank you, Íñigo.
Thank you. Okay. So, hello everyone. As you may know, in the BSc, we have like a team leading like our quantum research. However, there are also like some small teams who are also trying to open their small research lines on how to integrate quantum in the different fields. And my presentation is going to talk about one of these small teams, not the big quantum group leading the quantum research inside the BSc. So my team is accelerators and communicators. We are focusing mainly on classical resource management. And we decided last year that we want to start researching quantum computers and quantum simulators as an accelerator also, in the same way that we use GPUs. I think that right now this is a standard in the industry. Quantum computers are not meant to be used like as a one isolated device, but as an accelerator for different workflows and applications. So first of all, we try to find a problem that we want to solve, and we read a lot of papers, a lot of like different works that people have done, and we find this this project, which is basically from the Riken Research Center in Japan. They try to approximate electronic structure of a molecule or something like that. But what is interesting is the workflow they developed to do this. I'm going to try to explain a little bit how this hybrid workflow works, because it will be relevant for the rest of the presentation. So basically, they have two different stages. The first stage is the quantum stage. The first stage is creating the initial params, and then we have the quantum stage when we do some computation inside the quantum computer. This quantum computer will produce a result that will be consumed by the classical computer. In this experiment, we can use like, I think that more than 1,000 nodes in the classical stage, which is subdivided in different phases. The first phase is just configuration recovery of the result of the quantum computer. The second one, they subsample because the problem is too big, so they take just a small sample of the output produced by the quantum computer, and then they do a diagonalization. This is done among all the nodes. This is the only stage that is distributed, and it's just the diagonalization of a matrix. Finally, they took the result of the classical diagonalization and create new parameters for the next iteration of the quantum computer, and they iterate until they find the ground state of the molecule. So this has a problem. When you have a classical hybrid workflow, a quantum workflow, you have two different resources which are really different. You have the classical nodes and you have the quantum nodes. And you need both of them. So how people manage to get these resources? One easy solution is having two different schedules for each task. You have two different queues. So when you need the classical stage, you just submit your job, wait in the queue for the classical nodes, get a location, run your computation, you get the result, and then in the next stage, you do the same in the quantum computer. You go to the queue, request the allocation of the resources, wait in the queue, get the resources, do the computation, get the result, and again and again. Of course, this has a problem, which is you add a lot of overhead in just waiting in the queue for the resources. Other people have addressed this by just keeping the quantum resources during all the workflow. So they have the job in the quantum computer or in the controller of the quantum computer, and when they need to run the classical stage, they enqueue in the classical stage. This has a problem that usually the quantum computer is like it's not, you don't have as many quantum computers as you have classical nodes, so keeping for you for a long time this quantum resource is not like it's not a good idea. And then how the Riken guys solve this issue is just run the same experiment in parallel. When you are running the quantum computation in one population, at the same time you are running the classical computation in another population, so you run the same experiment twice at the same time without wasting resources. However, you need to run two populations, and sometimes you don't want two populations. So our proposal is to use dynamic resource management in the classical side of the resources. And first, let's try to explain what is malleability and dynamic resource allocation. So in the traditional resource allocation, as you might know, first you start a job, you enqueue, you take a given number of nodes, and you run your your job. After a certain amount of time, then you want to run another job, maybe it's you, maybe it's another user, but you don't have enough space for your job, so you just wait in the queue. So now the job 2 is waiting in the queue. Times continue, and now, for any reason, your job 1 may require less resources. However, as the allocation is static, you still have all the resources. However, you are wasting the resources, of course. Times continue, and now your job 1 just finished, and the job 2 can be allocated. With malleability, we can fix this by just shrinking or expanding our job. So as you can see, when the job 1 requires less resources, for example, to increase the communication efficiency, or just because you have changed the stage of your application and now you don't need the whole allocation, you can just shrink, let space for another job, and you improve your communication efficiency. At the same time, you improve the overall waiting times of the whole cluster. So this is malleability, and also, as I mentioned, you can also expand. If you need more nodes, you can shrink and expand. So to do this in the BSc, in my group, we are developing Dimmer. It's basically a library that uses the following stack. We use OpenMP, we use PERTE for the process management, and as a resource management, we are using Slurm. However, we are now exploring to make the Dimmer agnostic to the resource manager and exploring new resource managements, maybe Flux or whatever. Also, we have a kind of plugin which monitors the performance of the cluster, and we use Type for that. Now, a bit of marketing. I will show you how to use Dimmer. First of all, you have to init Dimmer. You just say how to initialize Dimmer. You create the first state, you initialize the stage, but also when you reconfigure, you have to recover the last stage of the last reconfiguration. So when you shrink, you have to recover the state of the nodes before the shrinking. So you use Dimmer init for that. Then you do Dimmer check. Dimmer check validates following a policy. A policy is just a logic which decides if you should shrink, expand, or stay. And based on that policy, Dimmer check will execute the action required. And finally, Dimmer finalize is the function which just free the resources and free the memory, and it prepares the program to end. So our proposal to fix the problem in the hybrid quantum classical workflows. As I mentioned, if you run the workflow inside the classical nodes, you will keep all the resources during the whole workflow. However, if you use malleability, you can shrink during the quantum phase and expand during the quantum phase. This is relevant, for example, because in the Riken experiment, the quantum phase lasts like 30 minutes to 1 hour. So in that case, it makes sense. If your quantum state is just a few seconds or milliseconds, this doesn't make sense. But if your quantum state is really long, and you do a lot of iterations, maybe you are wasting like thousands of nodes for more than 3 or 4 hours being just idle, which is not like a really good practice. Why we think our proposal is a good idea. No need to run the same experiment twice. Maybe you want 2 populations, but maybe you don't want 2 populations at the same time to be run. So this gives you more flexibility. Of course, it saves resources. You don't waste resources, and adapts to the system utilization. We have developed for this workflow different policies to showcase you how we can implement it. The standard, this just requests resources on premise. When the classical stage arrives, you will request the resources. You will have a little bit of waiting time. Then the greedy, it reallocates resources. As we know, the quantum stage has a constant time, so it's highly predictable when it will end. So for example, for the last 20% of the time of the quantum stage, you can preallocate the resources. You will be in the queue time during that during the last minutes of the quantum stage, you will get the resources. And then when the classical stage starts, you will have the resources ready for you. And the progressive is not only adapt the classical resources during the stage, but also in each iteration, because each iteration may have different requirements, as we will see later. So let's deep dive a little bit in the policies. So the first one is the standard policy. As I mentioned, there are two different stages, the quantum and the classical. For the quantum stage, first we launch the quantum computation. At the same time, we shrink the classical nodes. So for example, let's say that we have 20 nodes and we shrink to 4. Then we wait for the data. And when the data of the quantum stage is ready, we will expand. After the expansion is done, we can start the classical execution. Let's see how this behaves. So we have orange dotted lines, which represent when the quantum stage starts. And also we have blue dotted lines, which represent when the classical stage starts. These are real measurements of experiment running Mare Nostrum. And as you can see, when the quantum stage is executing, we shrink to 4 nodes, so we don't waste resources. And then when the classical stage starts, we shrink. We expand to the maximum of node. In this case, is 50. As you can see, also in each iteration, it takes more time. For the first iteration, I think it was just around 13 seconds. But for the second one, I will say that it's more than 30 minutes. So it's also an interesting fact. Then the greedy reconfiguration, as I explained before, it's the same idea. However, we wait for an arbitrary number of seconds, and we do the expansion. Then when we have the expansion ready, we wait for the data. This is not predictable because we said, okay, when there is only 20% of the time for the quantum stage, start expanding. However, we're in the queue, we can get the resources allocated at the moment, or we can wait in the queue for 10 minutes. However, they will be ready when the classical execution starts. And this is the same diagram. However, we can see how we got the resource earlier. The red arrows represent the quantum stage, and the yellow arrows represent when we allocate the resources. So as you can see, they are allocated before the classical stage starts, so we don't have to wait for them. And yeah, this is just the classical stage, which is really small. However, we got the resources for more time. And then progressive scaling, the design is exactly the same as the other ones, in this case, the same as the standard. However, as they have different resource requirements, we don't scale up to the maximum each time. We just scale to the resource that we need. So the maximum in the previous experiment was 50 nodes. However, right now, for the first iteration, we go down in the quantum state to 4 nodes. Then we scale up to 8 nodes, scale down to 4 nodes in the quantum stage. And then for the second iteration, we scale to 25 nodes. I don't know if I have arrows. Yeah, I have arrows. Oops. And yeah, as you can see, we save resources not only during each stage, but also in the different iterations. This is interesting not only for different hybrid workflows with real QPUs, but also with quantum simulators, because in this case, we are shrinking when we have the quantum stage. However, when we run a quantum simulator, we may want to expand in a bigger number than the classical stage. Also, the classical stage and the quantum simulator may have different constraints. For example, most of the quantum computers has a limitation that they require a number of nodes which is equal to a O of 2. So they can only be like 2, 4, 8, 16 nodes again and again. But for the classical, maybe the most optimal configuration is just 25. So malleability allows us to put the most efficient configuration on its different stage. And yeah, that was our research. And yeah, that was all.
Any question? I get to fetch the mic. Oh, sorry, Braden.
Hi. I imagine that like when you, in your script, you're requesting these additional resources, like there's not a guarantee that those resources are going to be available. So what happens if like, you know, multiple people have jobs and then they all try to request 100 extra nodes at the same time?
Yeah.
Does the script pause, or how does it get handled?
We have different, it's not explained in this presentation, but we have different implementations. The first one, the simple one, is, for example, in this case, we just wait for the resources, but we also have like an asynchronous request of the resources. So we wait for, let's say, I don't know, 1 minute, and if we don't get the resources, we start the classical stage with lower resources, and when we get it, we expand, and we continue with the classical computation. So yeah, it maybe depends on the situation of your cluster. For example, it will be interesting to give more priority for dimmer expansions. So as you are already a job allocated, it makes sense that you have priority in the queue when you expand. But in the case you don't have priority, you can just wait for the resources or start your computation, and when you get the resources, you expand and continue with the bigger number of nodes.
Thank you. And then I had one more. I mean, obviously this is for quantum resources, which are, you know, very scarce and hard to get your hands on. But there's also been a lot of discussion about like GPU resources and utilization. So is this same approach applicable to like sharing GPUs and being able to dynamically scale those resources as well?
Can you repeat the question? Sorry, I didn't hear you.
Yeah, sorry. Does the research you did on quantum resources, does that also apply to other scarce resources like GPUs?
Yes, of course. I mean, we usually work this with GPUs, and we try to mimic what we do with GPUs to QPUs. We find like workflows. I think, at least in what I have read, this is a really common pattern in quantum computing. Like you have like a closed loop on iteration of different stage. So yeah, but usually we apply this in GPUs. Is what we have done for years, yeah, in my team.
Thank you.
You're welcome.
So I have a question. Mm-hmm. So there's a project called Charm++. Not sure if you know that the project.
I think that I have listened about it, but I'm not confident about what it does.
Okay. So it's basically parallel programming approach. Mm-hmm. It's developed by Illinois.
Okay.
And so it allows you to implement certain capability on MPI code that allows you to grow on a string based on a trigger. And a string can interact with that and allow you to grow on a string. So it follows the same approach that you are following here. Now, how many applications they manage to use Charm++? There are not that many, so it's not that popular because the code, the algorithm in use, and there has to be capable to fully embrace this. Mm-hmm. I was wondering if you are seeing similar kind of behavior here. So how widely can be this use on generic code?
Yeah, so there are, I think I know which framework or library you mean. I think it's really difficult to try to convince people that they want to use malleability, because most of the times they say, why would I like to shrink, and also why would I like to shrink and also modify my code, so it's more work for me. So what we are trying to do is making our AP as simple as possible, so the footprint in the code is minimum. And also we are trying to focus on what gives to your code or to your application that make it like faster. So now we are, our most popular policy is the communication efficient policy, which means that if you shrink, your computation will be faster because you reduce the communication on some stages, and when you are like more computation bounded, you expand because you can parallelize a lot of more. So yeah, trying to convince people to use malleability is kind of difficult because they usually think, okay, as much nodes will be better, But I think that there are some interesting use cases when shrinking, expanding makes a lot of sense. Yeah, I don't know if I have answered your question.
Yeah. So one of the main use cases, this is from the design architecture point of view, at least for Charm++, is that rather than using job preemption based on suspension or checkpoint and restart, you can use preemption based on shrinking and then expanding when this is done. So you don't need to stop the job itself. You are just reducing the number of
yeah, we have different operational modes. One is checkpoint restart, which is basically checkpoint the state in disk, stop the job, and restart the job. We do this from a transparent point of view for the user. So for them, it's just the same job, but behind the scenes is we stop and restart. But we also have another operation mode, which is like MPA spawn, which is at the same time we have like the two processes, and we use MPA to communicate the new state to the expand, or to the, if we expand, we communicate the data required to the new nodes, and we don't have to wait the jobs, to kill the jobs. And if we shrink, we just reduce the number of nodes for the job.
Is there any more questions?
I have one.
Okay.
If no one has. First, technical communication. For those of you that are asking questions, please, the mic close to the mouth, because if you're talking here, nobody's listening. Okay? Thank you very much. So, following up Braden's question, I don't want to wait. Yep. So, as soon as I get my resources, then I go to the quantum stage, my node shrink, that's fine, because I want, my other me wants the cluster to be performant, and this means other jobs can get into the queue, and that's amazing, but then I will have to wait again. And it took me ages to get access to the quantum resource that we have, and then I will have to wait again, or using a lower amount of resources, which is hitting very hard on the time that my classical computing stage will take. How are users getting this? You already said that they are not willing to modify their code. I mean, we are users. I was one of them. I still am. So I know I don't want to modify my code. But is this really overall a better approach for the users, so that they are waiting overall less than before, than just by getting all the resources there idle, which for the sysadmin is a pain, but for me, I don't care?
Yeah, so I will answer this with two different situations. The first one is the one that we try to replicate or mimic. In our experiments, the maximum nodes were 50, but in the recent one, were like, I don't know if we 2,000 or 1,000 nodes, but were like a crazy number of nodes. So if you have like some quantum stage that takes like half an hour, and you iterate this workflow for, I don't know, 10 times or 20 times, you are wasting 1,000 nodes for hours. Maybe you don't care, but the administration system will ping you and will say, bro, you have to not waste the resources. So that's the first scenario. I mean, of course, if you are using 50, just keep the resources. It's not really a big deal. And the other one is, as I mentioned, if you integrate this with quantum simulators, they have different constraints. So maybe for your classical stage, you need, I don't know, 50 because it's more optimal, because of the communication you have in your classical stage or whatever. But for the quantum simulator, if you're running in the same job, you need to go to a POW of 2 number. So you have different requirements in the same job. You have to shrink or expand to meet the requirements on each state. So it's not about I have to wait, it's that if I want to run my experiment, I have two different ways. Expand and shrink, or split my workflow into different jobs and wait in the queue each time. With Dimmer, shrinking is free. You have a small overhead of 1 second, but you don't have queue times. And when you expand, you already have like some of the resources allocated, so you don't have to wait for all of them as you will do if you split your work, your job into different stages with different jobs. You just have to wait for half of them or whatever number you need. So it's an improvement for the user also in this case.
So on average, if I have to run 100,000 simulation, they will take on average the same amount of time, despite the pending time that there will be because I'm shrinking and expanding again.
Yeah, so if you shrink, the time is constant. I don't remember right now, but I think it depends on the number of nodes. From the number of nodes you are to the target nodes you are. So if you shrink to 2, it will be faster than if you shrink to 6. But it's constant and it's like really small overhead. Like if you have a workflow of, I don't know, 50 hours, this is overhead of 1 second maybe. And expanding, yeah, as you are in production, when you expand, you go to the queue. So you cannot predict the waiting time, but usually it's small.
Okay.
Yeah, so thank you for the presentation. So have a couple of questions. So regarding the job expansion, are you using native Slurm capabilities?
Yep.
Are you just submitting another job and just merging both jobs together somehow with Dimmer?
Yeah, we have 2 different Slurm versions. One is the official one that it's in production in Mare Nostrum, so you can just use Dimmer in Mare Nostrum as it is production, as in any other cluster, because we have support for a lot of official Slurm versions. And then we also have like a custom Slurm version for a special mode, which use like a nested Slurm, so you allocate all the nodes and then you have a nested Slurm version, so you expand a shrink. This is more for testing, but yeah, basically you have a production ready in most of the clusters.
And then regarding the job expansion, does Dimmer support scaled expansion? So you have to wait in the queue, right? You may not be able to get the 1,000 nodes that you need to continue your classical stage, but you may be able to get 200 nodes. Can Dimmer deal with it? Okay, allocate 200 nodes, and whenever the other 800 nodes are available, just incorporate them to the job.
Can you repeat the question, please?
So it's gradually expanding instead of just waiting for the whole expansion to be available.
Yes. Dimmer is like kind of modular, and the core of Dimmer is just the logic to how to use the resource manager, to interact with the resource manager to expand a shrink. And what you mentioned, this is the policy. The policy is the way you decide when to scale or shrink and how to do it. So we have some built-in Dimmer policies, but you can create your own custom policies. So one of we have is, for example, for the greedy one, no, this is not a greedy. So for the greedy one, it's not in this diagram, but how it's implemented is you request the maximum of nodes and you wait for half of the window. So let's say that the window is 60 seconds. So you wait for 30 seconds. If you don't get the resources, you try to expand to half. So if you request 50, you request 25. You wait for a quarter. If you don't get the resources, you request less resources to try to get it faster. So yeah, as it is really modular, you can do whatever logic you want to get the resources. Yeah, and you can do it in the other way. You can request like 20. When you get 20, you can request another 20. You can request, and you can scale up like in this way. For us, this is called the round policy, which is basically it's time double your size until you get your desired size.
Okay, thank you.
Any other question? Okay, thank you very much, Íñigo.
Thank you.